Today, we will introduce you to the world of prototype battery cell production. In this video, you will learn about the individual components of lithium-ion batteries and how they are produced. We all have this little companion with us. But do you actually know what's inside the battery? If you're interested, follow me to the AIT Battery Materials Laboratory, where the aim is to produce future greener energy storage systems in an industrially relevant environment. Welcome to the AIT Research Pilot Line, where you can learn about prototype cell production. Before we can start with the actual production, we need to know the individual components of the batteries. So let's have a look. The simplest version of a battery consists of two electrodes, an anode and a cathode, separated by a separator and all soaked in an electrolyte. The smallest example would be a coin cell, such as in your car keys or watch. Slightly larger energy storage systems, like those in your smartphones, consists of several layers of anodes and cathodes. While discharging, lithium ions are passing through the separator from the anodes to the cathode, while the corresponding electrons flow via the outer circuit. The total number of electrodes determines the overall cell capacity provided to your mobile device. Now, let's see how batteries are produced. First of all, a so-called slurry has to be prepared. A slurry consists of the electrochemical active material, a conductive agent such as carbon black, and a polymer binder for connecting the materials with a current collector. The mixing procedure, speed, and composition differ from production site to production site, usually going from higher to finally lower dry mass content. After the mixing has finished and the slurry has the desired texture and viscosity, it is transferred to the coating line. The gap between the knife and the current collector, where the slurry shall be coated on, determines the areal capacity. Why is this important? It is connected to the final purpose of the electrode. Are we producing a high-power or high-energy cell? Do we want to charge fast or store a lot of energy? Do we need a sprinter or a marathon runner? After both sides are coated and dried, next is the compacting process. The electrode is pressed and densified to a defined porosity, providing an optimum between volumetric capacity and pores for electrolyte penetration. This process is combined with heat treatment and is also important for the later application of the battery cell. Now that we have both electrode coils, we need to cut the electrodes. This surely is necessary for the pouch cell prototype presented in this video, but not in the case of cylindrical or prismatic cells, where the electrodes and the separator are wound together. Electrodes can be cut automatically via laser or using pressurized air, as in the AIT Research Pilot Line. The electrodes are set. We're ready to stack. You can imagine how crucial the alignment of the stack itself is. Some micrometers can make a difference. If the electrodes are not placed properly, it can lead to short circuit and even dangerous damage of the cell. The stacking process can be done with or without separator cutting. Conventional Z-folding is more commonly applied, but at a research institute, it can be more convenient using the single-sheet stacking approach. In general, the separator is placed between the anode and cathode to electronically insulate and avoid direct contact while ensuring proper lithium-ion flow. As already mentioned, the number of electrodes in the stack determines the overall cell capacity. At the end of the stacking process, the stack is fixed tightly and the current collectors are ultrasonically welded together with tabs to provide good electrical contact between and from the electrodes to the outer part of the cell. In the meanwhile, The outer shell, the pouch foil, is deep drawn to build the case and provide space for the stack in electrolyte. The stack is laid into the provided shell and sealed on 3 edges. One edge is left open to provide space for the electrolyte filling process. This process is another very important step in the overall cell production, mostly performed in sequences under argon atmosphere and vacuum to allow perfectly wetted electrodes without any overusage of sensitive and cost-intensive electrolyte components. After the electrolyte filling process, the cell is sealed on the missing edge, leaving some space to allow gas formation during the initial cycling. The first times charging and discharging of the battery cell is part of the formation process. This process is crucial for the cell as the individual components, after the electrolyte filling, do meet for the first time and the electrochemical system starts to establish. The cell is therefore charged and discharged with a low current several times under defined conditions such as temperature and pressure. During this process, gases may evolve as reaction products of side film formation. After the formation process is finished, the evolved gases must be removed. Therefore, the cell is punctured at the upper part and finally sealed, at best in an argon-filled chamber. Now, we've produced our first prototype pouch cell, ready to use, test, and cycle. In this video, you have learned about the prototype pouch cell components and the steps to produce them. Exactly that kind of prototype cell sits in your smartphone, with individual layers of electrodes separated by the separator in a similar way as we have together produced today. I hope you enjoyed this video and wish you a great day.